do the last talk of the conference. So for our very last talk, we've got Irena Swanson talking about primary decomposition of powers of ideals.
Thank you. First of all, I would like to thank the organizers. This is an amazing conference. The whole preparation, email communications, everything happens pretty much immediately. Thank you so much for organizing it, for being so responsive to everything, for great hospitality, and all the special effects that you provided, and also for all the great math that you brought in one place. So thank you all. And then I already spoke about Karen yesterday, but again, I want to emphasize, of all of you in here in the room, I've known Karen the longest. I also have Karen number 1. How many of you have Smith number 1?
There's a big picture.
You know Irish number 1? So there's yeah. So who has Smith number 1? That's quite a few people. Yeah. So the other thing that I didn't say yesterday about Karen, I'd like to emphasize is that she has her head on right. When she sees something that's nonsense, she will point it out. And thank you for doing that too. This is an important thing that makes the world go forward more slowly. Anyway, happy birthday, Karen. Thank you. I chose to talk about the topic that's closest to Karen. I haven't done something for a few years in this area, but I want to emphasize this part here. And at the start, I will talk with finite and linear and maybe linearly bounded world. So, you know, that's something much more graspable than and then I will weave into this that primary decompositions rule, whatever that means, and then the end will be all opposite, because the world is not all finite and linear. So, but and then maybe this my talk also has a subtitle with with a view toward computation or effective computation or computational complexity. So I started graduate school in the 1980s, and here was the state of the world in the 1980s. I knew a few other things, but I will emphasize the finite and linear. So the first one is Noetherian and primary decompositions. So every ideal in an Noetherian ring has a finite primary decomposition. Great. So finiteness. And actually, I don't know when to prove that. But another finite thing is from Rees in 1956. He proved that for, I should say, R is always Noetherian. Every ring is Noetherian, and I is an ideal.
And commutative.
Yes, commutative, what identity? I is an ideal in this I. So Rees proved that for every I, there is a finite set of valuations. Am I writing big enough? Okay. There's a finite set of valuations that determine the integral closure, not just of I, when you first have evaluations, y with finitely many suffice for the integral closure of I, but it's actually even for integral closure of all powers of I. So that's another finite result. And there's another thing due to Rees in 1961, I think. If you start with a Noetherian, so this of course means Noetherian local ring with maximal ideal M. This has reduced completion. Okay. So in the literature, these rings are called analytically unramified, but you know, I've been working on this area for so long, and I have to keep looking what analytically unramified looks like. But reduced completion, I understand. This has reduced completion if and only if, for every, or alternatively, there exists an M primary ideal I such that, for which there exists a constant C such that for all integers n bigger than or equal to C, the integral closure of I to the n is contained in the n minus c's ordinary power of I. So here's an example of linearity. Other example of linearity is so Brians and Skoda in 1974, and then Lippmann, Sate, and Lippmann, Tessier, and Lippmann, Tessier in 1984. These are two separate papers. If you start with our regular ring, so they prove this in greater generality. I'm just giving a quick result here. If R is a regular ring and I is degenerated, so the number of generators of I is D or possibly smaller, then the integral closure of n plus D, or I to the n plus D is contained in I to the n. So, and this is for all n. So here's another linear result similar to this one. Then back to finiteness, Brodmann in 1976 proved that the set of associated primes of all the powers, so you fix the ideal I, and you look at the set of associated primes of all the powers, this is finite. He did not prove that this eventually stabilizes, but he did prove that the union of the set of associated primes of integral closures of all the powers is equal to the set of associated primes of some integral closure, and this is true for all sufficiently large M. So here's some finiteness results, and then I did it the wrong way. This is Ratty Brodmann. Brodmann did it 3 years later, also for modules, and he proved that this eventually stabilizes. So I would just write n to the I and n. So this is a finite associated. I'll just write similarly, and it stabilizes. Right, and then I will do just one more result. Katz-McAdam. This was 1989. For every I, there exists a constant C such that for all integers n and all ideals j, if you take I to the, and then for all n, I to the n colon out j infinity, or I should say nc. I to the n times c, did I say there is c? Yes. I to the n times c power colon j infinity. So that means that we take the nc power of I and remove all the primary components that that a power of j is contained in them. So this is stabilizes nc plus 1 colon j. Sorry. I'm getting ahead. I to the n colon j to the nc is I to the n colon j to the nc plus 1. So these are some of the linear results that I really admired and I thought they were cool. Makes the world easier to understand. It's linear. I also, of course, knew some other things, such as the Hilbert polynomials, but they're not linear. But okay, so yeah, well, I'll emphasize the finite and linear. And then late 1980s enters tight closure. And as you all know, tight closure proved a lot of things in a very efficient way. It was made great progress on the Bianchi-Scola theorem and so on. But there was one basic problem. Does it commute with localization? Does tight closure commute with localization? This was not known back in the 1980s or 1990s or even early 2000s. We know that Brenner and Monsky, so I'm jumping ahead a little bit, Brenner and Monsky proved in 2010 that no, it doesn't. But we didn't know that back in the 1980s, so we try to chip away at it. So now here's a problem. So question. For every ideal I, so now I need characteristic P. So R has characteristic P. Does there exist a constant C? Okay, constant C. Such that for all positive integers E, there exists a primary decomposition of e to the e, so e Frobenius power of I. So the number of components may depend. So we've got e sub 1, e sub 1, e sub 2, q e sub n sub e. Such that, and we know that primary decompositions are not necessarily unique, so but can you choose one of them such that for all E and all I, if you take the Q E sub I, if you take this primary component, look at its associated prime, raise it to the e to the e Frobenius power and also to the c ordinary power. This is contained back in Q e sub I. So that means that we can control the primary components of these from below. They don't get too small too fast. So if the answers, I'll call this problem this here. If this property holds, let's call this property linear primary decomposition for Frobenius. And one thing that you can prove, if yes, if this is an easy exercise, you can work it out. If yes, then tight closure commutes with localization at principle, commutes with localization, tight closure of I commutes with localization as principal multiplicatively closed sets. So if you just invert principal multiplicatively closed sets. Oh, we're making progress. So let's try to, can we prove this? So then there's also the corresponding,
So wait, I have one question. So the question is for what you fix an I and ask the question.
right,
Yeah.
yeah. So there's also corresponding linear primary decompositions for ordinary powers. And one advantage for ordinary powers that played a huge role in most of these proofs is that we have Riesz algebras. And Riesz algebras have pretty nice behavior, but there's no such good Frobenius Riesz algebra. All right. So, so here's some progress on this. So, so there are several cases. What happened then? In 1992, I proved this for, yes, the dimension, yes, so I proved linear primary decomposition for ordinary powers.
Wait, actually, I have another question about the definition of the linear primary decomposition. There's two different for all e's. Are they the same e or different e's?
No, I don't need it here.
Okay, thanks.
Sorry. For ordinary powers, if the dimension of R mod I is less than equal to 1, or I did it a little more generous, I can do it for some prime embedded primary components if the height is at most 1 over the in. But then we came on to Katzmann, 1996. He came out with an example such that the union of associated primes of R mod e to the e, as e varies, this set is not finite. So here we're trying to achieve something linear, but something non-finite comes in, which makes quite a few arguments not so easy. Then came a paper of Karen and me in 1997. We analyzed this Katzmann's example. So for Katzmann's example, we do, well, he only has one element. Katzmann's I, the linear primary decomposition for Frobenius holds. Not only we prove that it holds, but we also have an effective C. And Karen and I also did it to have, if R is a polynomial ring modulo a monomial ideal, and I is also a monomial ideal, then we proved linear primary decomposition for ordinary and Frobenius powers, and with effective C. We can get it from exponents appearing in the ideal. And then I had the result in 1997 where I proved this more generally linear primary decomposition for ordinary powers. And then the same year we also had with Heinzer. We also did linear primary decomposition for ordinary powers, but in restricted rings, but we did it very differently. We proved some other special properties with restricted rings. Why did I leave room here? Because the same paper also proved some uniform Argentine type, uniform type results. And this was in the style of 1992 paper by Humeke. And then there was also, if R is a polynomial ring, and I is homogeneous, then there exists C such that the regularity of R mod I to the N or I to the N is less than equal to C times N. So here's another linear thing. And these are also, I have some linear primary decompositions and intersections, uniformities, intersections. So this one here, I should say that this was influenced, there was a preprint by Karen Chandler for many years, and she finally published it in 1997. She was limited to when the dimension of R mod I was at most 1. A similar restriction at what I needed here. All right, so far, there aren't that many effective results here. There's this existence. So my goal, I said, view toward computation. Even if you have linear bounds, if you know that something is finite, how do you know where you would stop? And that's perhaps not that, it is not that helpful.
Irena,
Yes.
could you say a little bit more about the regularity? I'm looking at the associated prime, and everything kind of looks like consistent, but then I think of regularity in terms of betting
Right,
tables
yes.
and such, and I don't think of it in terms of primary
Right, this is
decomposition.
not primary decomposition now. So that paper has more than one
just
thread.
a different direction.
Yeah,
Okay,
yes.
great. I was missing the connection.
Yeah,
There it was.
But with these uniform type results, if you just come up with some resolutions and then manipulate them in some uniform way. So that's how it is.
Cool.
All right, and then of course there's the famous Einlassensfeld Smith in 2001. This was, again, a lot of these things before, there was type closure, there was integral closure, release algebras, valuations. There were lots of things happening, but here there's very different method. So first they started with our affine regular domain over C. They could prove this much more generally, but again, P is a prime ideal. So they do the linear primary decomposition for the minimal prime, so but the effective one, if you raise the symbolic, so the n times height of P, this is contained in the ordinary power for all n. And they prove this also more generally. You can do reduction to other rings containing other regular rings containing Q. But this was a huge jump from all the other results, very effective. And they came up with the asymptotic multiplier ideals and sub-additivity property played a huge role. So that's a very different method. And of course, then there was Hofstede and Humeke doing the same with type closure. That was also 2001. And then 2018, it was Ma and Shi. For a mixed characteristic using protector modulus. And again, I'm stating the simplest results. All of these papers are much broader. So I'm still talking about finite and linear, so I'll just talk through some finiteness and linearity. So there was ideal adic topologies. I will not write down everything, but the results of CATS, 1985, Schenzel, 1985 and 86, and Hakaba, 1989. They determined, they gave characterization when fix J to infinity, so we fix I, an ideal I and J. If you take this sequence of ideals, when this topology is equivalent to I added topology. So the result has something to do with dimensions after completion. I will not write down that, but I think in 2000, I proved that when when this topology, these two topologies are equivalent, then the equivalence is linear. And then the other thing that has already been mentioned is a linear Artin approximation. I will not state what this is, what the statements are, but there are lots of people who worked on this. Maybe the first version of linear Artin approximation is Vilto Gabrielov, then Doran Popescu, Mark Skivakovsky, Hickel, Lejeune Jalabert, and Delfino and I also have a version of linear Artin approximation, and I'll end this in 2006. Guillaume Ron proved that, so lots of cases were proved, but he said linear Artin approximation false in general. Okay, so there are lots of linear results out there, but not all of them are true all the time. Okay. So I have woven in a little bit of primary decompositions. I'll come back to this, but now I think it's time to move away from linear approximation. I exhausted almost all of my linear results. Maybe we should face the world, and it's not all that linear. Here's a status in the 1980s. There's status that I was not aware of back in the 1980s or even 90s. It took me a while. So then let's go back to, what do you call this? Let's go to nonlinear world now. So Grete Hermann, I'll write her first name. She has two N's. 1926, Grete Hermann was a student of Emil Edder. Then Abraham Steinberg in 1974. And then more constructively, Van den Ries and Schmidt in 1984. So what did they do? They're given positive integers m, d, and n. There exists a function b depending on these, such that for all ideals I generated by at most m elements in a polynomial ring in n variables over fields of phase of fields, with all degrees less than or equal to d, then the following are bounded above by this B of MDN. So there are a lot of things that are bounded above. I'll just go over a short list here.
I mean, are your F's homogeneous?
No, they don't have to be homogeneous. If I want to do regularity, then they would have to be, but for primary decompositions or ideal containment. So one of the things that is bounded is an ideal containment in I. So in other words, what I mean is coefficients in ideal. So what I mean is if G is contained in I and degree, then if G is contained in I, then we can write the G as a linear combination of AI, Fi, and the degrees of A sub I can be taken to be, well, you can't just do this, because if I multiply G by a zillionth power of a variable, then I should increase it, so I need to add degree of G here. So this is ideal containment. Another thing is number of associated primes of I, number of generators of these primes, degrees of generators, same for primary components. And there are other things too. But one thing I should have said, this B here, this B is doubly exponential in N. So it's maybe I think it's d to the d to the n, or let's just say 2 to the 2 to the n or something with some other coefficient. So it's their exponent is in the second level up there. I think it has d in there. There were a few problems in Greta Hermann's proofs. She assumed that all fields have certain properties. But really, I was like, okay, she had some mistakes, but really, do you need double exponential? That's way too big, right? So it's very easy to find examples for this ideal containment where it's singly exponential. And I'll write it down. If you take this ideal x1 minus 1, x2, x1 to the d minus 1, x2 to the d minus x1, x3 to the d minus x2, x sub, sorry, I think I'm doing that. X, there's no d here. Here's x1 to the d minus x2, x2 to the d minus x3, x sub n minus 1 to the d minus x sub n. Okay, that's a fine ideal, but now let's throw x sub n to the d in here. Okay. So now, if you look at, there are no solutions to this. The x sub n would have to be 0, so they're all 0, but they can't be 0. So we know that 1 is contained in here. So according to this ideal containment, well, we should be able to write a linear combination of this, and the coefficient here, no matter how you write it, coefficient has degree d to the n minus 1. I mean, you could make it bigger, but it cannot make it smaller. So singly exponential is fine. One thing I was very surprised at, why would Greta Hermann, a student of Emmy Noetherian in the school of Hilbert, worry about bounds, right? Like, it exists, why do you need an upper bound? But they were worried about it already back before there were computers and computer programs doing it. And one advantage of establishing these upper bounds is if you know that the degrees of all of these have this upper bound, then you convert this into a linear algebra question. You write each AI as a linear combination of monomials, of all monomials of degree up to this. And then it's a linear algebra problem. It's a huge linear algebra problem, especially with the double exponential thing. And this is not an effective thing. Which of these double exponential functions will be suffice? But anyway, so there was an interest in this. There still is an interest. And then it was in 1982, Meyer and Meyer, they worked in computer science, complexity theory, group theory kind of stuff. And they found there exists a doubly exponential family. So Caroline was vindicated. There might have been errors in her proof, but at least that happens. There exists doubly exponential ideal for ideal membership. So this ideal membership is you need double exponential coefficients. Then Barr and Stillman analyzed this paper in 1984. And they also have syzygies are doubly exponentials and therefore also regularity. So you can homogenize your ideal. Originally it's not defined homogeneous, but you can make it homogeneous. So all of these are doubly exponential. So I was staring at these and so, you know, I really like my world to be finite and linear, but you can't ignore reality. So some years before that, I was looking at permanental ideals. So we all know that if you take a generic determinantal ideals, it's a prime ideal and the ring mod, that prime ideal has lots of properties, Macaulay, normal, all the good things, right? But if you look at R mod even 2 by 2 permanental ideals, so permanents are instead of, you don't have to worry about pluses and minuses, it's all plus. So it should be easier, except that computing permanents is NP hard, whereas computing determinants is polynomial time. So that computation of permanents is computation hard, determinants is easy. Primary decompositions of permanents are hard, primary decompositions of determinantal ideals are prime, you're done. So there was this, I'm trying to weave in that primary decompositions tell you that when something is computationally hard, maybe primary decompositions will reflect that. So that was my idea here. Of course, I had to look at these my ideals. And what I proved is that, so there's a family of them, and the number of minimal primes over these Meyer ideals is polynomial. It's first of all, it's linear in the number of variables. It's linear, okay, that's good. The number of various variables, but polynomial in degree, degrees of the generators. And then the number of embedded primes. This is where it gets interesting. Okay, and this work was 2002 and 2003. The number of embedded primes is at least a polynomial in n, but it's also at most a doubly exponential function in n. So I can explicitly provide a lot of examples, but then the way you do primary decompositions, maybe you have some short exact sequences, or maybe you colon and add. And so you know that some of them where you colon, whatever is associated to the colon is also associated to your ideal. but if it's associated with I plus something, it may not be associated with an ideal. So eventually I converted this family into a recursive family that worked perfectly for these double exponential ones, but I failed to eliminate redundancies. It's very hard to describe. If ideals are monomial, it's fairly easy to, it's somewhat doable to determine primary decompositions. These ideals are binomial, so it's not that bad, but it's still, there are lots of binomials in there and hard to compute certain intersections. Some intersections are easy, but some are not so easy.
So can you ask a question? You're talking about the Meyer ideals?
Yes, yeah.
And are you saying you have examples where it's polynomial and examples where it's doubly exponential, or just that?
No, this is, so I should have written this, this less than equal to that, which is less than equal to this. Because this is a Meyer family, I should say, they depend on the number of variables and the degrees. So it's, inside this family, the number of minimal primes is linear in the number of variables with polynomial if you change the d. But then for embedded primes, we have a lower bound. I think it's a polynomial degree 3 in variables. But, all right, so I was on a roll. Primary decompositions determine the world, right? Except that then in 2016, Humica's birthday party, McCulloch and Pieva proved the following. That's it. They proved that if R is a polynomial ring, and I should say this one. If P varies over prime ideals in polynomial rings over a field, then the regularity function of P is not bounded above by any polynomial function in the degree of the ambient ring mod P, the multiplicity of these rings. So there's no polynomial, so it might be exponential, maybe double exponential. Okay. So thinking about how primary decompositions, like have a lot of associated primes and then something bad is happening computationally. This is saying that the regularity of P, which is what helps us compute resolutions and determine so many things. So this is really computational thing, saying that regularity P fails on a prime. So primary decomposition of a prime is pretty easy, right? So here that really shattered my how the primary decompositions roll with don't. Okay. By the way, this of course is a counter example to the Heisenberg Gaussian projection. So then sometimes when you something reality is well, I had to rethink my reality, right? But the fact is they introduced two new methods, two new methods or tools maybe. One of them was step-by-step what word? Homogenization. Homogenization. and the other one was Rees-like algebra. All right, so this is the ordinary Rees algebra. If you add the inverse of t, that's the extended Rees algebra, but they added t squared. So what they did is they took the Meyer ideals, they did the Rees-like algebra of the Meyer ideals, and the defining ideal of that is a prime, but that prime might not have been homogeneous, so you can't really do the regularity. So they had to do some very careful step-by-step homogenization and a few extra steps, and it's really a beautiful construction there. But so I needed to understand what is happening with this Rees-like algebra. And so now I will not go in chronological order. So the upshot of those experiments that I did with Rees-like algebra is a joint paper with an undergraduate student, Jesse Kim. We published this in 2019, and maybe this section has subtitle primes behaving badly. So what we proved is that we construct a family. We construct families of prime ideals in polynomial rings. So they're primes. Prime decomposition of a prime is very easy, but the number of associated primes of R mod the second power, or in some cases, all higher powers, or so sometimes all n. So this is not bounded by any polynomial function.
I don't understand R and P, and you just have P squared, that's a finite set. So you mean for all in? But you want to do this for all?
Oh, so R mod P squared certainly has finitely many associated primes.
Right.
The number may depend, not by any polynomial function, in the number of variables, so in the dimension of the ring.
Oh, I see.
Yeah. So the number of variables can go up, but then this that goes up to or p to the n. So in some cases. So I don't know that I will be able to cover our full construction, but so I will just work it out. I'll work out this result on just the first family of examples. So first of all, this B, we prove that this BMTN is, oh, I didn't write it here. Is bigger than or equal to 3 to the n over 3. So n is the number that is the dimension of 3, the dimension of R over 3. So that's dimension of R is n. And the other thing is, if you know the Ananyan Hoxter bound, so EMD, let's call it capital N, EMD. So this is a it's a primitive recursive function that depends on m is the degrees, the number of generators and p is the degree. And this function bounds above number of associated terms of in arbitrary polynomial ring, arbitrary number of variables. So we don't count the number of variables, mod an ideal with m gens of degree less than equal to d. So we proved that this function has to be at least, I have this one, no. So sorry, I don't remember this one. No, sorry, it's correct, because this one, it is 3 to the square root of 2m and then minus 1 in the exponent. I don't know if you can see that. So it is exponential and something. All right, so let me go through the first example, and I won't be able to prove all that. First example, let's start with polynomial ring in 3 variables, and we want to take the kernel. So x sub I goes to t to I plus 2, so t cubed, t to the 4th, t to the 5th, and p is the kernel of this map. So this is a prime ideal. Huneke in 1986 proved that for all positive integers bigger than or equal to 2, the associated primes of the ambient ring and nth power are exactly, of course, p is associated, but then the only other thing that could be associated is, so this is height 2 in a polynomial ring of 3 variables, so x1, x3. And so the only other thing that could be associated is a polynomial that is an ideal of height 3, but the quasi-homogeneity will have to be this one, and it is for all n. So now what we do is we essentially take this step-by-step homogenization, but a much simpler version that already existed in, say, in Eisenberg's view, Eisenberg's book. It's an exercise in one chapter. So what if you have a ring A and you map A, you have expected polynomial. So x and t1 through td are all variables, and phi of x is the product of these b variables. So we call this splitting. We also allow exponents, but things are a little easier without all exponents 1. So what happens then is that the primary decomposition, so if I apply this to one of these, if you start with a prime here, if so few associated primes of the image of phi is, so it's either just p extended if x is not in p, and otherwise there are whatever the base ring is, replace. So if x is in p, then we get v primes where you take the old in p, you replace x by v sub I. So then under this splitting, you get v associated primes, but they all have the same height. So if we go back to this example, and I will split x1 into a product of v1 variables and x2 into a product of v2 variables and x3 into a product of 3 variables, then what happens is that under the ambient ring, so our join all the t's, t of p and all the powers, the number of associated primes, the minimal prime translates exactly over, but all the others, we get v1 times v2 times v3, and if v1 is equal to v2, which is equal to v3, as v, then we get a prime ideal in 3D variables with v cubed embedded primes. Okay, so this is not definitely not linear, but it also not exponential like what we claim there. It's polynomial, and the degree of this polynomial is 3. The 3 is determined by the number of variables in the associated primes. So what we need is a method that will add more primes into the prime ideal, and this process doesn't add more primes. It doesn't add more variables into the primes, it just makes more primes. So we need, the more variables we have in an associated prime, the higher this degree will be. Okay. So here's an easy method. We take p plus, so I'll just work with this particular p with 3 variables, and I will add my m minus 3 variables. So now this is in a polynomial ring in m variables. So, and the associated primes, so this is q, we call this, associated primes with r mod, s mod, higher powers of q. Well, of course, there's just q, but then there are all those t sub I, sorry. We have we still have the x's, and now we also have all the z's. Okay. So now there are m variables in here, and now if you split each variable, so we have m variables, each of m variables into distinct product of distinct, let's take them all the same, distinct v primes. Then we get p of q is a prime ideal so the height stays the same. Height is still m minus 1. The height 2 plus m minus 3 is m minus 1 in polynomial ring in m times v variables, and the number of embedded primes of the k adjoined all the t's now mod p q higher powers is the product, so it's v to the n. So the more of these m's you add, then the higher the degree. So now we have degree n. All right, so you get some, I should stop. You get, for example, you can have a prime ideal of height 4 in 19 variables with 500 embedded primes. Height 5 in 18 variables, fewer variables, but higher height, 729 variables. And then height 10 in 22 variables, 2048, so 2 to 11. And then we have another starting ideal, which we got actually with these like algebras. And they actually have a pretty interesting construction of spreading that. Yeah, and they're height 5 in 18 variables, 768, height 6 in 22 variables, 2,560. So this computational part is not Yeah, that's crazy. All right, so I should stop here.
Any questions, Irena?
I would just want a clarifying question. I think it might be a typo on the board. But if not, then I don't understand. So when you split x1, x2, x3,
Yeah,
and then you're computing the number of associated primes there, you want to join t's, the u's, and the w's, right?
right, yeah,
Okay,
yeah.
Yeah.
So here, this was a previous one.
right.
and Maybe I should have called this T sub 1, 1,
Right.
T sub 1, T 1, T sub 2, 1.
Okay, I thought that you
Yeah.
were joining all of them, but I just
Yeah.
wanted to check.
So, so since where are people, or what is the reason behind thinking about bounding all of these things? No, it feels that that we try to bound these things so that we see whether we're able to do explicit computations. No,
That's
you mentioned one of another students. No, like it seems like it goes back to.
so there was still much conjecture that then it was proved by Anand and Hoxter that projected dimension of an ideal in a polynomial ring can be bounded above just in terms of the degrees and the numbers of generators, but it's independent of the number of variables. So there are lots of people worked on that field. So there are lots of ways why people want to bound things and projected dimensions like that.
Other questions? All right, well, thank you, Irena.